With Admira Fusion, Foco presents the first purely ceramic-based restorative material worldwide. It is based upon the innovative combination of tried and tested nano-hybrid technology and ORMOCER technology. In the following, we will show filling a Class 1 cavity with Admira Fusion. Cavity preparation, cleaning and drying are followed by the application of the adhesive, here Futurobond U, which is used in cell batch mode. After activating and opening of the single-dose blister, the adhesive is applied homogeneously to all cavity surfaces and rubbed in for 20 seconds. The adhesive layer is then dried off with dry, oil-free air for at least 5 seconds. 10 seconds of light polymerization are necessary to cure the layer completely. The first increment of Admira Fusion is directly applied into the Class 1 cavity and adapted. But before the curing process starts, we have a closer look to the inside of the material. With the help of the transmission electron microscopy, it is clearly to identify that Admira Fusion contains a mixture of different sized glass particles, nanoparticles and ORMOCER resin. The colored illustration depicts the single elements more obviously. The three main elements of the filling material are all based on silicon oxide, a unique structural characteristic. We will explain the mechanism behind the pure silicate technology within the following scenes. Starting point is the atomic structure of one glass particle. A silicon oxide network is the base, where the silicon atoms are colored in black and the oxygen atoms are colored in red. The silicon atoms are tetrahedrally surrounded by oxygen atoms, which connects to further silicon atoms. Additional metal atoms are also embedded into the network to increase the radiopacity of the material. They are marked in green. The surface of the glass particle is modified, shown by the yellow spheres. The special coating is done by a silanization process which takes place in an upstream reaction. For this purpose, methacrylic silane compounds with a double bond are used. They enable the connection to further double bonds, what means further elements of the matrix. The double bond is highlighted in red. The next matrix element to take a closer look to is a nanoparticle. Compared to the glass particles, they are much smaller, but from structural considerations they are very similar. The base is also a silicon oxide network, where the silicon atoms are tetrahedrally surrounded by oxygen atoms. Furthermore, the surface of the silica nanoparticles is silanized as well, indicated by the yellow spheres. During the process of polymerization, the coating enables a chemical connection between the different matrix elements of Admira Fusion. The red highlighted double bond is responsible for the connection. The just shown glass particles and nanoparticles are embedded in the ORMOCER resin. After light polymerization, all of the shown matrix elements build up a stable three-dimensional network, in which all the solid particles are immobilized. The unique ORMOCER resin is also based on a silicon oxide network. The silicate backbone of the ORMOCER resin is highly cross-linked. Additional methacrylate groups are contained, which are depicted in purple. The red highlighted double bonds are the linking units to the other matrix elements. The so-called multifunctional ORMOCER resin enables a quantitative fixation inside the polymer network. In the following, we illustrate the synthesis of the unique ORMOCER resin. What happens exactly during the process of producing such an ORMOCER resin matrix? Based on a silane precursor, the organically modified ceramic particles are created by hydrolysis and condensation reactions. The ORMOCER resin stands out due to its highly cross-linked structure in its core, on the one hand, and the tremendous amount of linking units, see the red marked double bonds here, on the other hand. Back to the macroscopic view. The following working step is light curing of the first increment of the filling. Due to light curing, the recently introduced elements react with each other. A stable, three-dimensional network is created. Nanoparticles, glass particles, and ORMOCER resin get strongly connected. Once again, we zoom into the process during the light polymerization. The single, surface functionalized elements come into view. Glass particles are shown in beige, nanoparticles in yellow, and the ORMOCER resin molecules in blue. The blue light of the light curing unit initiates a chain reaction. The double bonds react with each other to chains, or a network respectively, which is marked red here. Now we apply and adapt the following increment. And light cure again. Finally, the material is shaped, finished and polished, which results in a functional and aesthetic posterior restoration. The use of Admira Fusion leads the user to many advantages. A high biocompatibility is achieved by the pure silicate technology. This means the three main ingredients, glass particles, nanoparticles and ORMOCER resin, are exclusively based on silicon oxide networks. There is no use of conventional methacrylate monomers. Because of the high degree of cross-linking of the specific chemical elements, Admira Fusion has still higher biocompatibility than conventional composites. The material has a very low shrinkage while curing, because of the high filler content of 84% by weight and because of the ORMOCER resin elements. These are much bigger in comparison to conventional methacrylate monomers. See now a comparison of volume decrease caused by curing. On the left-hand side, conventional methacrylate monomers and the unique ORMOCER resin elements on the right. The shrinkage of the ORMOCER resin is many times smaller. The following graph illustrates detailed values of shrinkage. Admira Fusion has a value of 1.25% by volume, which is out and away the lowest shrinkage compared to all market-relevant restorative composites. An additional parameter, amongst other things connected to shrinkage, is the shrinkage stress. Here, Admira Fusion also scores when compared to competitive products, because of its very low value of only 3.7 megapascal. Very good stability values are of vital importance for durable fillings. A high surface hardness correlates directly with high abrasion resistance, luster, shade and shape stability. The surface hardness of Admira Fusion is high-leveled, with 141 Vickers microhardness. A further physical measure is the edge stability. High values reduce the risk of breaking off edges, the so-called chipping. Admira Fusion is convincing with a very good value of 172 Newton. Especially in the posterior region, it is important to create stable fillings which resist the high chewing forces permanently. Finally, we present a clinical case. The initial situation is an insufficient amalgam filling, a Class II restoration at tooth 1-4. Firstly, the amalgam filling is removed completely, followed by drying the operating area and application of the matrix. Further steps are application of the adhesive, dispersing the excess solvents, and the closing light polymerization. The application of Admira Fusion starts with building a distal wall, which is then light cured. The matrix is removed and the additional increments are applied and also light cured. The last picture shows the finished and polished restoration. Function and aesthetics are restored completely.